And the things which I'm going to present here are in a focus on my attention. About half a year, maybe this whole year, I'm working with the problem of approximation of positive polynomials. Some of these results are already delivered, some of them are firstly delivered here, and also I'll give some further direction of research in this direction. And I will start with a very well-known fact that the cone in a finite dimensional space is coincides with the convex hull of its extreme rays. And this is a direct corollary from the Cleese theorem, which was proved in 1958, which says that if K is a closed convex locally compact subset of a locally convex topological vector space, and this space do not contain straight lines, then it is recovered or it coincides with the convex hull of the union of its extreme points and extreme rays. And of course, it's closed convex hull. Here on the slide, you can see the illustration of this theorem, Cleese theorem, for the finite dimensional case. Just to visualize what I said, this space is our K. And by this big A, B, D, we denote the extreme points of this space, and they are the symbol xk is used, and little a and little b red half lines denote the union of extreme rays on this picture. So k is, as you see, the union, the convex hull of union extreme points and the extreme rays, and in the case when we are in infinite dimensional space, here is also a closure. The problem of such kind of theorems for linear operators is a long-standing problem of functional analysis. And to the present moment, there are several classes of linear operators for which the approximation problem or recovery problem is solved. They are referred to names of Phelps, Morris, and their pupils, and dated about 1960s. And what about the case when we consider the space of nonlinear operators? Nothing, as far as I know, was done till the present moment. And let me start with the precise definition of extreme ray. We call the open half line of convex subset A an extreme ray if any line segment which joins elements x and y of this set lies entirely on ρ, provided that there is at least one inner point of segment xy which lies on ρ. As I showed, the union of extreme rays is denoted by this symbol extra k, and also I will use the standard notations, which are the following. CQ is the Banach space of real valued continuous functions on compactum Q. CK plus is a part of CQ which contains only positive functions. CK prime, as usual, is a dual Banach space, and CQ prime plus is again the positive part of CQ prime. The motivation for this result is follows from two interesting facts. So the first of them says that the extreme ray of the space of continuous Banach space of continuous functionals on Q is exactly the positive multiples of Dirac measures. And the second statement says that in the space of continuous functions on CQ, each element, each positive element, can be approximated by the pointwise limit of linear combination of Dirac measures with coefficients. This can be rewritten in this form. So here a question arose, and what can be said if we work, as I already said, with the space of linear operators which are acting between Banach spaces and the positive. Of course, we talk about positive linear operators. And the answer was given by Professor Anthony Wickstead in 1981. The precise formulation of his results will be given a little bit later. I just show you here the main statement of this theorem, just to pay your attention to the fact that this linear positive operator acting between E and F Banach lattices can be also represented as a linear combination. And here you can see, instead of Dirac measures, some linear operators, which I will define later, but they are called lattice homomorphisms. It is just written in this form to visualize that this is the one line of investigation. And now I said a term Banach lattice. Thanks to Professor Kusraeva, yesterday he determined this term. But as far as we are going to work in these spaces, I will determine them. Firstly, saying that our goal of investigation was to obtain generalization of the previous theorems for the homogeneous polynomials acting between Banach lattices. As it was told yesterday, Banach lattice is an ordered vector space where for any two elements there exists supremum and infimum, and Banach, it is, vector lattice, and Banach lattice is a vector, is a Banach space, which is also a Banach lattice, where the ordering is has the property of monotonicity. And all classical Banach lattices, Banach spaces are Banach lattices with ordering introduced pointwise. If we talk if we work in function spaces such like CQ, LP, and the ordering is introduced pointwise when we speak about the space of sequences. I suggest to keep in mind all the results that I'm going to present right now are obtained for or arbitrary Banach lattices, but I prefer and suggest to keep in mind LP and LQ spaces each time when I pronounce Banach lattice. This will help for simplify the understanding. Of course, we will lose some generality here, but it is not a problem for a whole general understanding of the problem. Okay, now I guess I have to introduce the main object of the investigation. It's homogeneous polynomial. So the mapping mapping pi is called homogeneous polynomial if it is representable as a restriction of the some n-linear operator to the diagonal. This n-linear operator is called generating for P, and in case when it is symmetric, it is unique for this polynomial, for this concrete polynomial, and it is called associated for P, for polynomial pi, and denoted by P check. Also, a class of polynomials which we are working with is a positive polynomials. Polynomial is positive if its associated multilinear operator is positive. And one more, the notations. We use this notation to for the class of n-homogeneous polynomials, and by here plus is denoted the part of polynomials which consist of positive polynomials. The ordering is introduced by the following way, very easy. One polynomial is greater or less than another if the difference is positive. And just to give again clarify the notion of polynomial, I give this example. Here what we do, here as I promised, we take instead of the target space L0 space, and then we consider the linear operator T from X to L0 and construct a new operator pi by the following way. Each value, we take x from x, and each value tx from x, we raise to the power n. So constructed operator is homogeneous polynomial. We can easily check this if we write the associated multilinear form, and if we restrict it to the diagonal, we will get exactly this polynomial. So these are not so abstract notions of polynomials. And one more class of polynomials which is necessary for the investigation, which is very good investigated. These are orthogonally additive polynomials. Okay, what are they? A homogeneous polynomial is said to be orthogonally additive if it is additive in any pair of disjoint elements. Here, let me say what means disjointness for function spaces again. Two functions are disjoint if their supports do not intersect or intersect on the measure on the set of negligible measure, or what is the same, their product is equal to 0. So again, notations, the space of orthogonally additive polynomials is denoted by this symbol. The ordering again is introduced by the same way. Yeah, the cone of positive polynomials is denoted by this symbol. So yes, and homomorphism. Now, at the beginning of my talk, I introduced a part of the Wickstedt theorem where the homomorphisms were used. So the precise definition of lattice homomorphism is the following: that a linear operator which preserves all lattice operations is called lattice homomorphism. Here I used one of the lattice homomorphisms. It is modulus, absolute value. But these definition look to be not very difficult, but it is not good for understanding. That's why I suggest to an example, a typical example of lattice homomorphism. It is a weighted shift operator, which is defined as follows. Here, a weight is a positive measurable function W, and here you can see the shift operation. This means that the change of variables is made. So such form of operator, which is called weighted shift operator, is a typical lattice homomorphism, and we denote by this symbol the space of all the set of all lattice homomorphisms. Again, this is already familiar for us. Definition of the notation of the cone of positive linear operators, and as usual by E prime we denote the dual space to E. So finally we came to the situation when I can formulate the Wickstedt theorem, which says that we already saw this, that the cone of positive linear operators is a pointwise norm-closed convex hull of lattice homomorphisms. And now I have to define what means a convex hull. Let me just say that the convex hull of set A can be written as this guy is called convex combination of the elements of A. Convex combination can be substituted with linear combination in the case when A is a conic set or cone. This result was obtained by Wickstedt, as I said, in 1981 in this paper. And now we can formulate the first main result of this research, which was obtained in 2024. I will show it all and start with the third condition. What we obtained? We obtained that an orthogonally additive polynomial, positive polynomial, can be is a pointwise norm-closed convex hull of the powers of degrees of lattice homomorphisms. The third condition and the second are almost the same, but in this case we work with the orthogonally additive polynomials with values in real space. And the first condition is the first condition says that the linear operator defined on the power of a vector lattice is a pointwise closed convex hull of its extreme points. And by the way, for the proof, of course, I will not give the detailed proof, even not detailed proof. I will just say that from first condition to the second condition, we come due to the very interesting result according to which the linear operator, the space of linear operators on the power of a vector lattice is isomorphic to the space of orthogonally additive polynomials on space E. This is the due what these two conditions are equivalent. So I just say that this result was proved in maybe in the end of 23rd year and published in 2024. And further on, it was very interesting what to do in the case, as you understood, the case of orthogonally additive polynomials is a class of polynomials. It is not the whole class, and it was really interesting to us what will happen if we work with polynomials, not orthogonally additive, but general polynomials. And it turned out that it is not enough to use the powers of homogeneous lattice homomorphisms. I'm sorry. It turned out that here we will need the product of the powers of lattice homomorphisms. To do this, I just show you the definition. Yeah, we define a polynomial Q by following way. Here, of course, this is done in general case. It is done for the arbitrary Banach space F, but for the example, for making the multiplication easy and understandable, I use L0 space instead of F in the target. So defined polynomial Q is an n-homogeneous polynomial, which can be checked very easily. I wrote here the generating multilinear form, and you can see if we restrict it to the diagonal, we will get exactly what we defined. So the result, I'll show it again, all three points, all three bullets, and we'll start again with the last one, saying that each positive homogeneous polynomial, not necessarily orthogonally additive, can be approximated as a pointwise norm closed convex hull of the powers of lattice homomorphisms. The second bullet is just the same with, again, just the same with the third bullet, but with here we work with real valued polynomials. And again, the first bullet says us that a linear positive operator is pointwise norm closed convex hull of its extreme sorry, I always say points, but I mean rays, extreme rays. This result was finished, I guess, at the beginning or maybe middle of August, and is submitted to the journal, the same journal. I'm waiting for their answer. And now, also, I have a little time to present what was done before. At the beginning of not beginning, in the middle of 2023, the generalization for the analogous of Crane-Mill theorem for homogeneous polynomials was obtained. You can see it here, which says it says that a pointwise a set omega, which is pointwise order bounded operator convex and pointwise order closed, can be represented as the, let me say, pointwise norm convex hull, I have to say here, operator convex hull of it and now extreme points. This result was obtained, as I said, published in 2023. The precise definition of extreme point is given here. I will just say that we call an extreme point of a convex set A a point which has the following rule, maybe. If we extract this point from the convex set, the set remains to be convex. As you all already understood, this symbol is used to notate the set of extreme points. And I will skip the definition of operator convex hull. It is just the same with the operator, with the convex hull, with only one difference, that here we use, instead of reals, we use multiplication operators. So what next? The question is, because right now I presented three theorems which generalize Crane-Millman's theorem for, not generalized, which are the analogs of Crane-Millman theorem for homogeneous polynomials and Klee's theorem for homogeneous polynomials, and for a class of one class of homogeneous polynomials called orthogonally additive polynomials. And so the question, what is next? We found that in 1962 by Choquet there was proved a theorem according to which a closed convex cone in a locally convex topological vector space is if it is well kept, then it is the closed convex hull of its extreme points. Here are some definitions. A cap is defined like it follows. Almost, it is similar with extreme point. If we extract this cap from the space in convex space X, the space remains to be convex, and the set Z is called well kept if it is the union of its caps. And further on, in 1969, Asimov obtained the following result. He proved that a well-kept convex closed set. Now we talk about he talks about closed sets, not cones. This is what he won. So a well-kept convex closed set in a locally convex space is a convex closure of a set of its extreme points and extreme rays. So our next destination to be reached is to get the analogous of Asimov's theorem for homogeneous polynomials, which will generalize everything what was obtained right now and presented here right now. These are the Klee's type theorems for homogeneous polynomials, Choquet type theorem, and Klee's type theorem for homogeneous polynomials. So I hope we will succeed in this direction, and thank you for attention.